Oh, does it like record the whole thing or like just the audio?
It's says it's recording meeting. I don't know. I think you're recording.
Yeah, is the video also being recorded? I
Yeah,
mean,
I
I
think
haven't
that.
recorded anything in Zoom before, so I mean,
Yeah, I haven't. I think you're good.
yeah. Sorry, guys. I do you guys want to start first?
Yeah, sure.
Yeah. Do you
Yeah,
want to share the screen?
Yeah,
Or the
sure.
yeah,
Well,
yeah,
first,
sure.
I guess I'll introduce myself.
Yeah.
My name is Blake Melton from UW Stout. I'm a manufacturing engineer, sophomore here.
I'm Ethan. I'm a mechanical engineer from UW Stout. And we also had a third partner, Riley Goen. She worked with us on this problem uh, as well. So
Yeah,
Yeah.
I'm Shalman Guru from Seneca, and I'm in EMA right now, electromechanical engineering. Yeah, that's it.
Sure. So I can share my screen and we can go through our lab report and kind of talk about what we did in the project.
Sure, I'll make you the host now.
yeah, so basically, Sarman sent us um, some information on the robots. And from that, we had a couple things that we needed to calculate for our end of the project.
There.
Yeah,
Oh,
yeah. You guys can start now.
All right. Sounds
sweet.
good.
Yeah.
All right, so this is our lab report for our coil project, and the background here. So we were given this robot from the Seneca group, and we were put in charge of finding the physics behind it and working with it and a few other things. So we were given some information from Sarman here, and we used that to figure out the movement, the velocity, the max speed of the robot, and yeah. So I don't know if you want to take over on
Yeah, so we
kind
kind
of
of have our
details.
process here. I won't get too in depth, but we first had to solve for the cycle time. Sarman gave us like an example of this. Sorry, we got some people in the background over there that can't
Nah,
get
it's totally fine, guys. That's okay.
um yeah, we were given this cycle time from Sarman, and we basically had to solve for a theoretical time, what we based off like the other specifications of the robot. So we assumed some other things like acceleration, and we were able to find a pretty reasonable time of like 7.206 seconds. So that was good. And then we had to solve for force of the grippers in order to hold on to the puck, the robot. And I don't remember what numbers we had. Numbers are further down,
Yeah.
but we were able to find that it's about 1.19 newtons from each gripper to hold on to the puck, and we were able to solve for that.
So on the screen right now, this is the our calculations that we use to find the total time of the graph. And you can see right here we have our acceleration of 1.75, which we assumed. And we used that, plugged it into constant acceleration formulas, and then ended up with the total time of 7.206, which is what 1% error from what we were given in the
Yep.
Seneca group.
If you look on the left side there too, that was the graph that we used to like track the movement. So it's a velocity time graph. So first we start by accelerating, and then based on like the robot specifications, we kind of assume maximum speed. So we accelerated up to that top speed, and then we stayed at that constant velocity. Then we decelerated to a stop, and there were four Y movements, so up and down, and then two X movements across for one cycle time. And we found a cycle time of 7.206, which, like Blake said, like 1% there.
The next picture here. So this is our the part of the problem where we solve for the force on the gripper. So we knew the mass of the puck, and we were able to use that and set up a free body diagram there to figure out the forces that were actually acting on the puck. So we found that there was two forces clamping the puck together, and then we had the puck's weight, obviously, and then we also had friction that was holding against the puck when it was moving up. So we used our equations, sum of force in the x, sum of force in the y, and then we had a couple friction equations, and then we were able to get that the force that it required to clamp down on the puck was what does that say down there?
0.1962.
0.1962. Yep. Yep. So that was pretty simple compared to the velocity one that we saw for earlier. But it's still kind of cool and interesting to like figure out the actual forces when the puck's clamping and how it's moving and other forces that are acting on it too. And then the last one.
Finally, we just kind of tried to find like maximum velocity that the arm could while still holding on to the weight. We used 1 second. We had to use some work energy principles. So we were able to find the work based off the displacement force, and that's how we were able to find our maximum velocity. Yeah.
Yeah, I think that pretty much sums up our work. I stop sharing my screen here.
Yeah, thank you so much, guys. I think I should. Hold on. I don't have the things ready.
That's all good.
All good.
I can share my screen now, right?
Yep. I think I got to make you the host again.
Oh, yeah, sure. Oh, I can do now.
Yep, you got it.
Yeah. So, this is not it. So I just want to like show you guys a basic outline of the lab that we did, and then like the lab report that I made. So okay, this is no lab 5 first. So yeah, this is actually the lab 5. What we basically did in lab 5 was like the programming of the sequential control of the pick and place robot, right? So this is the basic programming in lab 5, and then what we did in lab 6 was an advanced thing. So what happens is in this lab 5 is this: we program the robot to like so there. Hold on. So we just programmed a robot to do the basic pick and place thing. And what happens in lab 6 is this advanced form of this like this. We program it into 3 modes: the cyclic mode, the automatic mode, and the manual mode, where like if it is in manual mode, we have to control all the movements manually. In the automatic mode, when you push the start button, then the pick and place robot like does this movement until the user gives a command to stop. But in cyclic moment, what happens is like the robot just moves the number of times that the user inputs. So that's basically like the overall summary of lab 5 and lab 6. And uh, this table is like really what's it called, like the simple explanation of what happens, the detailed step-by-step explanation of what happens in the lab. And I think I sent you guys the table too, right?
Yep.
Yeah. So these are all the sensors: the open limb, left limb, upper limb, which which are not that important right now. But what's sorry, have you guys ever like programmed any PLCs before?
No,
I
I
can't say
haven't.
I have.
No, right? So these, how do I explain them? So basically this is the PLC tags that we use, and what happens in PLC programming is the tags define how the programming is done. So these are the various tags that we use in while PLC programming the PLC. Like close limb, this is the sensor for closing the gripper. Like open limb is the sensor for opening the gripper. Upper limb goes up, lower limb goes down, right limb goes right, left limb goes left. Basically, these are the sensors present in the uh, what do you call the automatic the robot, and these are the prompts that we use to like give the sensor instructions that okay you are going to be activated now and you perform the function, something like that. And uh, so you see the addresses here like I and Q and M. These are basically like, so I means like input, and then Q means output, and M means it gets stored in the memory bit. And yeah, so these are the PLC tags, and this is the program, actual programming that we have to do in the PLC. So these are the various networks that we have to build. Um, if you check out the lab 6, yeah, this is the lab 6, and we also have the same thing, the step-by-step table of the actions that happen in the lab. And these are the, like PLC tags, the same thing. These are the same thing. So that's just the difference in between these and the lab 5 is what you see after number 36. See, we still have 6 more tags, right? So what these tags mean in lab 6 is like in lab 5 we didn't have the cyclic mode, right? So these are the tags we use for cyclic mode. See, like it says cycle PD, like cycle push button, cycle mode, counter reset, sequence active. So these are the tags that we have added on top of lab 5. In lab 6 we make it more like make it add the cyclic mode. And this month, the only difference in the network as well is the cycle, like push button. It's the normally closed cycle push button that we use here. Um, just how to explain this? I'm not very good at explaining this to you guys, but I mean,
You're
like
all
you
good.
guys
Yeah,
get,
you're
We're
doing
following.
good.
yeah,
Yeah,
you guys get what I mean. Like these are like basically
yeah,
the same, like lab 5 and lab 6. Because you guys um, haven't done like PLC programming before, it's very hard for me to like explain the network, right? So
Yeah,
these
we get that.
networks are like basically the programming language for the PLC, and like uh, it all depends on what type of um, what type of like instructions you use in these codes that define like how the robot works. So there's not much difference in the networks between lab 5 and lab 6. Just some additional codes, like you can see here, like the cycle mode, like the thing covered in red circle is just the difference between lab 5 and lab 6 in the code. This code is the same, like this is the timer. Um, so it says like this is for the timer for the what they call the gripper, and we also use another timer that that indicates like the stop time after the plug is left down, because sometimes what happens is the plug may not be dropped properly, right? So we have to give them a like bit reset time, like 3 seconds, so that the plug gets released properly and it can go back safely. Otherwise, if the plug is like stuck in the gripper, then like when it goes up, like then accidents may happen, right? So this is the time we add in the gripper, and so this is the cycle code. I don't know what it's called, like cycle something. This is basically like the command prompt for the cyclic mode. It says like 3 cycles, right? This is the cycle code, and then it says this three means like the movement of the robot completes after 3 seconds. No, after 3 movements. So it says like initial call means call everything, then stop the movement after 3 seconds, like 3 movements. So these are all the same for the manual mode, auto mode, and cycle mode. That's basically like the difference between lap 5 and lap 6. And I also want you guys to show you, like look at the report. This is the report one that I made for lap 5. And hold on, maybe this is like a bit more easy to explain for me as well. So these are the basic step by step for the last five. When we press the normally open push button, then uh, this is the initial like mode of the robot. It's at home position, and then when the start condition for the robot is when we push the start normally open start push button, and at that time, like the auto mode and stop push button are on, then the robot is at home position. Right? The end condition for this step to end is when the step to start and then the stop TV gets off. What happens is the gripper goes down. So the robot moves down from the home position until the lower limb sensor is triggered. The lower limb is the sensor that's present in the robot, and when the sensor is triggered, it signals that the puck is ready for picking, and the gripper, the jaw of the gripper comes down. And basically, like this table is just explains the step-by-step process of the picking puck movement in detail. And these are some of the observations that we can see from the lab. Is that we also use an SMI. We didn't use an SMI. We didn't use an SMI which we programmed ourselves, but the SMI was like already pre-programmed by the professor, which he gave us. And SMI is basically the control system for the robot. So we can't control the robot in our computer, right? So SMI is the output unit that's present in the PLC, and it's a small screen. It's a small screen. Hold on. Yeah, this type of you guys can see this, right? So this is attached in the PLC, And then what happens is we can control the movement of the robot from this computer, like from this screen. This screen is like touch sensitive, so it works like a control panel for the robot. So we have to program this as well. But in lab 5 and lab 6, our professors already gave us three program code which we could just use to control the robot. So that's what that's what this thing says. Like we integrated the PLC as well as the HMI, and then we check if the sensors were working properly or not. Then the purpose efficiency, then the sequence logic. Sequence logic is basically if all the steps happen one after another or not, and then that was done correctly. And yeah, we use the HMI interface for starting and stopping the sequence. And yeah, so after this lab, we were able to demonstrate the basic sequential control of the pick and switch robot. And for lab 6, this is the code that I made. Yeah, it's everything's the same. Just the difference is like it has three modes: automatic mode, cyclic mode, and the manual mode. What's the manual mode? This is the manual mode, and manual mode is a simple mode. You just have to control every movement of the robot, and it has 6 buttons to control every movement. It has like, moving up button, down, left, right, opening, gripper, and closing gripper buttons. So there's also a manual mode button before. So what happens in the HMI screen is when you start first, I should have taken a video to explain you guys more easily, but like when you like download the program in the HMI screen, what happens is there's a home screen at the beginning of the at the beginning, and then after you getting the home screen, like there's three modes. It has like manual mode, automatic mode, and cyclic mode, and then you can choose from which mode you want to move forward. And this is the manual mode. So the use case for like one of the use of having manual mode is like it's useful for debugging and aligning the robot to a specific position. And sometimes the robot might get stuck in the middle or like it might do something that you don't want to do. So you have to reprogram everything and then make the robot work efficiently. So for that, like if you want to debug it, like the manual mode is the best way to do it. In the automatic mode, what happens is everything that happens in the manual mode, it just is automatic. And every time, the automatic mode ends at the home position so that it's safe and consistent. And then so this is the ladder logic breakdown. So when we start the start push button, then the auto mode is initiated, and then what happens is the process, like the movement of the robot. And the thing about auto mode is like it doesn't stop unless the user gives command to stop. So, and every time when you start, if the robot is in the middle of the movement and you start stop, it doesn't get stopped here. It goes, does this thing and come back to the home position at the end. So, and in the cyclic mode, you have to put the number of cycles that you want the robot to complete, and after that, something like cycles, the robot comes back to home position. And like, so you guys might think, what happens if somebody stops the robot in between, like, even if the cycles are not completed, right? So in the cyclic mode, no matter what happens, like the robot doesn't stop in the middle. So if you have given an input to the robot that you want it to complete 5 cycles, even after you try to stop the robot after 3 cycles, it won't. It still complete 5 cycles and come back to the home position, and it always returns to the home position at the end. And yeah, it has a counter. Oh, like the timer that I showed you for the number of seconds for the gripper to hold or release the puck. It also has the cyclic mode also has a counter to count the number of cycles that the pick and place robot complete. And these are like the step by step feature observations. And yeah, the conclusion, the manual mode is efficient for debugging and the precision task. Automatic mode is efficient for continuous automation, and cyclic mode for repeated operation. And yeah, that's it, guys. I, I, I hope I didn't make it. I hope you guys could understand it, right?
Yeah, we got it.
Yeah. Do you guys have any questions?
Huh?
Do you
I
guys
don't
have
think
any?
so. It looks pretty cool. I mean,
Yeah,
Yeah,
we
you
don't
guys
understand
have.
all of it, but yeah, I think it looks pretty cool though.
yeah.
Yeah, you guys have the video of the thing, right? How the thing works.
Mhm.
Mhm.
Yeah. I think that's it. Yeah. So maybe I think that was what we're supposed to do, make a video. Oh, yeah, I tried
Is
to
that
stop
good for the
that.
presentation?
Yeah, if you need anything
So
from us, just let us know.
yeah, I already prepared a presentation as well, but I just have to add the video and then like finish it up. So